The problem is from GATE 2020 mathematics paper, question number 46. The problem given is, if gamma of t given by the curve 1 divided by 2 times e to the power of 3 pi I t, where t belongs to the interval 0, 2, closed interval 0, 2, and integration over gamma 1 divided by z square times e to the power of z minus 1 dz is given as beta pi I. Then beta is equal to, correct up to 1 decimal place. So the NPTEL reference to solve this problem is module 6 lecture 5 of complex analysis. The title of this lecture is Residue Theorem and Applications by Dr. P.A.S. Sri Krishna. He is from Department of Mathematics, IIT Guwahati. Even you can watch this lecture using this YouTube link. So now coming to the solution, we solve this problem using residue theorem. So firstly, let me write what is given. So given the function f of z as 1 divided by z square times e to the power of z minus 1, and the curve gamma is given as gamma of t equal to half times e to the power of 3 pi I t, where t belongs to the closed curve 0, 2. So what does this means is, we can see easily that modulus of gamma of t equal to half. That means the curve gamma of t is nothing but the circle with the center 0 and radius half. That is, when we take this is the complex plane with the point half at this point approximately, and this is minus half, and this is I by 2 minus I divided by 2 approximately. Then the curve gamma of t is given as the curve with the circle with the curve gamma of t is nothing but the circle with the center 0 and radius half. This is gamma of. But the question here is, in which direction it is, either clockwise direction or anti-clockwise direction. One can check that by substituting the values of, or one can check the by taking the values t from 0 to 2, in which direction you are getting. By taking t equal to 0, you get gamma of t as half. That means this point. When keep moving, t is pi by 3, you get gamma of pi by 3 as minus I divided by 2. That means this point. So when you keep moving from 0 to 2, the value of t, you are getting the values of gamma of t in this direction, anti-clockwise direction. That means the curve gamma of t travels along the circle mod z equal to half in the anti-clockwise direction. But the question here is, how many times the curve gamma travels along this circle mod z equal to half. So for that, we simply check by taking some particular values. So we can say gamma of 0 equal to half, that can be seen easily. And whereas coming to the point gamma of pi by 3, it is minus I divided by 2. And similarly, by taking the values gamma of this is 1 by 3, not pi by 3. Earlier also I said pi by 3, I think that is 1 by 3, not pi by 3. So by taking the value of gamma of 1 divided by 3 is minus pi by 2, plus pi by 2. and gamma of, sorry, this is the point minus 1 divided by. So the, and in between this, the value of, so for the three image of I divided by 2, we can take the midpoint of 0 and 1 by 3. That is nothing but 1 divided by 6. That is equal to I divided by 2. That we don't need actually, but just for your clarification, at the point 1 divided by 6, the value of gamma 1 by 6 is I divided by 2. So simply by moving the point from t from 0 to 2, we are getting, and gamma of 2 by equal to 1 divided by 2, and whereas gamma of 4 divided by 3 equal to 1 by 2 again, and gamma of 6 by 3 equal to 1 divided by 2 again. That means the curve gamma travels along this circle, margin equal to half price. Since we can see the image of gamma at the points 0, 2 divided by 3, 4 divided by 3, and 6 divided by 3 are same. That means when you travel, when you keep changing the values of t from 0 to 2, taking this as 0 and this as 2. So at the points 0, 2 divided by 3, 4 divided by 3, and 6 divided by 3. So when you keep changing the values t from 0 to 2, the value of gamma of t keeps changing. The curve gamma travels along this circle 3 times. That you can see by changing the value of t from 0 to 2. That means, so we can say, so yes, t travels or t changes varies over varies from 0 to 2. The curve gamma of p travels along the circle, margin equal to half price. So now by using the residue theorem, we can write, by residue theorem, we have integration 1 divided by z square e to the power of z minus 1 dz along the curve gamma. That is what given, is equal to 2 pi I times the sum of residues of f of z, or residues of the function, 1 divided by z square times e to the power of z minus 1 at the singularities. Singularities A. Let me write the singularities are A, where A are the singularities of 1 divided by z square times e to the power of z minus 1 inside gamma, or since it is given f of z, so let me write f of z only. So f of z of f of z. So now looking at the singularities of these points, which can be seen easily, that the singularities of these points are the points at which the denominator becomes 0. So it can be seen easily that the singularities of f of z are 0 to n pi I, where n belongs to integers. Since at the points 0, the denominator becomes 0, can be seen easily, and to become the term e to the power of z minus 1 is 0, the only such points z are nothing but 2n pi I for all integers n. But the question here is, out of all these singularities of the function f of z, how many does lie inside this closed curve gamma? That can be seen easily by this graph. Since the since we can see the obviously the points 0 lie inside this closed curve gamma, and coming to the second singularity 2 pi I, that is that lies outside the closed curve gamma. So similarly we can see the next singularity minus 2 pi I and the rest of all the singularities lie outside the closed curve gamma, out of which the only singularity lie inside gamma is 0. So we can write integration 1 divided by z square e to the power of z minus 1 dz over the curve gamma is equal to 2 pi I times residue of f of z at the point 0. So now we can if we can calculate the residue of the function f of z at the particular point z equal to 0, we can simply see the answer for this problem. But since there are many methods to calculate the residue of any function at any singularity, such as by using any formula, or the standard method is to by looking the coefficient of 1 divided by z in the Lorentz series expansion. So we follow the Lorentz series expansion method. So now for the residue of f of z at z equal to 0, we find the coefficient of 1 divided by z in the Lorentz series expansion of f of z around z equal to 0. So now we can write the function f of z given as 1 divided by z square times e to the power of z minus 1 as 1 divided by z times, this is as z plus z square divided by 2 factorial plus z cube divided by 3 factorial plus and so on. This can be written as 1 divided by z times, sorry, z square times, or okay, let me write one more step. So 1 divided by z cube times 1 divided by 1 plus z divided by 2 factorial plus z square divided by 3 factorial plus and so on. So now to look at the coefficient, now look at the coefficient of the term 1 divided by z. In this Lorentz series expansion, we do the following: 1 divided by z cube times, I can write this as 1 plus z divided by 2 factorial plus z square divided by 3 factorial plus and so on whole inverse. So now by expanding this series, we get 1 divided by z square times 1 minus z divided by 2 factorial plus z square divided by 3 factorial plus and so on plus z divided by 2 factorial plus z square divided by 3 factorial plus and so on whole square plus the higher terms z divided by 2 factorial plus z square divided by 3 factorial plus and so on whole cube plus and so on. So now to just look at the coefficient, is it only z cube? Yes. So now to look at the coefficient of the term 1 divided by z, it is just enough to look, since we have already 1 divided by z cube outside, so it is just look at the coefficient of the term 1 divided 1 look at the coefficient of the term z square inside this bracket, that is, so this 1 divided by z cube as it is, next 1 plus z times some term that we don't need. Next, coming to the z square term, we get as minus 1 divided by 3 factorial plus from the second power we get this as 1 divided by 4 factorial, that's it, plus z cube times some terms. Since in the next expansion the smallest degree will be z cube, so there does not exist any z square term, so this the coefficients ends here. So this in total we get as, so residue of f of z at the point z equal to 0 is, we can see easily that minus 1 divided by 3 factorial plus 1 divided by, sorry, this has 1 divided by 4 only, 1 divided by 4, that is minus 1 divided by 6 plus 1 divided by 4, this has 1 divided by 12. So hence in total we have integration over gamma 1 divided by z square times e to the power of z minus 1 dz equal to 3 times 2 by I times the residue as 1 divided by 12, that is equal to 6 divided by 12, that is pi I divided by 2, that is equal to 0.5 times 5. Here one can have a doubt that why it is written 3. The residue theorem tells us that 2 pi I times 1 divided by the residue at that particular point. Why? But why it is written 3 here? That comes from the given curve. Since z equal to 0 is the singularity and gamma is the circle with radius half and center 0, which is traveling 3 times around this the singularity z equal to 0 3 times, which can be seen from this given curve. So we have the point z equal to 0 is a singularity of this function repeating 3 times inside this closed curve gamma. So that's why we write 3 times 2 pi I times the residue at that particular point, that is 1 divided by 12. So in total we have this as 0.5 times pi I. But the question it is asked that the value of beta, that is can be seen easily as beta equal to 0.5. Thank you.